So 30, you've got a sample of size 9, so n is 9, from a distribution whose variance is known, sigma squared is 25. And the hypotheses are these. The null is that mu is 20, and the alternative is, what is this, right-tailed, left-tailed, or two-tailed? It seems to be neither. It's an equal sign in there. It's not a mistake. It's not a typo. We want it to be an equal sign to make our thought process simpler, you might say. And in fact, when we have an equal sign, it's called a simple hypothesis. And the Neyman-Pearson lemma is stated in terms of simple hypotheses. This is a simple hypothesis. The Neyman-Pearson lemma is stated in terms of that. Actually, I guess I could point at both of these and say these are simple hypotheses. That's an E there. SES for plural of hypothesis. Simple hypotheses there. Because it makes this problem simpler to think about, is the point. And it also makes the Neyman-Pearson lemma simpler to think about and also simpler to apply. If we do the more typical thing with the alternative and put a greater than sign or a less than sign or a not equal to sign, that's called a composite hypothesis. The alternative hypothesis contains more values than one value in that case. The test statistic uses sample mean x bar. We're agreeing to reject the null in favor of the alternative if x bar is greater than 25. Okay, and there's the picture here. Let's go ahead and redraw that picture. If the null hypothesis is true, which we always assume when we're doing our hypothesis testing, then the sampling distribution of x bar is going to be centered on 20. And look like that, say. What is this? Yes, I could just call it the distribution of x bar, as we typically do actually in our textbook. But for emphasis, as many other people do, they put the word sampling in there to emphasize it is coming from a sample. We're computing a sample mean. Sampling distribution of x bar, make it a capital X bar because it's a random variable, if the true population mean is 20. Centered on 20, it's unbiased, right? We're doing random sampling. What is its standard deviation? What is sigma sub x bar? It's the square root of the variance of x bar, square root of sigma squared over n is sigma over square root of n, and for this problem, that becomes 5 over square root of 9 is 5/3. So if I'm trying to make the picture extra accurate, and it actually looks like the book didn't make it as accurate as they could have. This inflection point right there, it's going to be at 21.6 repeating. And this other one down here is going to be at 18.3 repeating. Just trying to make the picture a little more accurate. We are agreeing to reject the null. The decision is reject the null in favor of the alternative if x bar is bigger than 25. Say right there. Therefore, the probability of a type 1 error, where you reject the null when it's true, would be the chances of being greater than 25 when your true sampling distribution looks like what you see here. It's going to be a very small number. Choosing the rejection region in that way is going to completely determine what alpha is. Alpha, the level of significance, is the probability of a type 1 error. That area, which will be small, is going to be the probability of a type 1 error. This is the rejection region. Also called the critical region. Technically speaking, if you want to write it as a set, is the set of all numbers bigger than or equal to 25. Should I use a lowercase or uppercase here? I think I'll use a lowercase. Set of all x such that x is greater than or equal to 25. Maybe call that C. C for critical region. Go ahead and calculate alpha where we asked for that. Yes, in part C it says find alpha. Alpha is the probability of a type 1 error. Again, it's also called the level of significance. It's the probability that you're in the rejection region. You could write that as x bar is greater than or equal to 25. You could also write it as x bar is an element of C. That would be another way you could write that probability. Why am I doing that? Because sometimes the name in Pearson lemma is written that way. Yeah, it's actually often the best way to write it is an element of, because in the abstract, the name in Pearson lemma, the critical regions can be higher dimensional sets in 2-dimensional space or 3-dimensional space or n-dimensional space. And so it's not so easy to write the critical region as an inequality. Maybe. Still might be able to, but maybe not. Yeah, this is the same as x bar being greater than or equal to 25, given that mu is 20. Written as a conditional probability, but then when we calculate it, we don't bother with the conditional probability notation. We standardize, convert to z by subtracting the assumed value of mu and dividing by sigma over square root of n. 5 divided by 5/3 is going to be what, 3? In my head. So this is the probability that z is greater than or equal to 3, which is, yes, pretty small. Less than 0.005. Okay, yeah, I could do a lower that's not minus infinity, but there we go. I did 1 minus. About 0.001. Alpha is very small. Another part of the problem says if H1 is true, what is the distribution of x bar? H1 is 28. Mu is 28. The alternative hypothesis. If that's the truth, then your sampling distribution is centered at 28. A little closer to 25 than 20 is. Maybe about here. The standard deviation is still about 1.7. So I want my inflection point here to be at, well, 26.3 repeating, which might be right about there, say. And the other one would be at 29.6 repeating. So that's the sampling distribution of X bar. Excuse me. If mu is 28. Which is the true sampling distribution? Nobody knows, because nobody knows what mu is, right? This is all theoretical math, but it's theoretical math for practical importance. This does help us make decisions about things still, even though we don't know what the true sampling distribution is, because we don't know what mu is. No matter what the alternative is, the rejection region is still the same. And by the way, notice, yes, I did define the rejection region as the book does by saying we're rejecting if X bar is bigger than 25. And that helped us find alpha. You also can go the other way. You also are sometimes can be given an alpha, like say 0.05, and you can figure out the rejection region. You can reverse the process, right? You can, if alpha were 0.05, you use z sub 0.05 to figure out a point where the area to the right under a standard normal curve is 0.05. That would be 1.645, I think, right? Make the area to the left 0.95. This is like for a 90% confidence interval, 1.645. So you can go the other way is all I'm trying to say here, and that was a brief example. We're also asked to figure out beta and the power. Beta first. Beta is the probability of a type 2 error, and the power is 1 minus beta. Probability that, what is a type 2 error? That's when you fail to reject the null when you should have. You're not in the rejection region, even though the alternative is true. So in this case, in terms of inequality, that's probability that X bar is less than 25. And the alternative is that mu is 28. And do the calculation. Don't subtract 20 like I just accidentally did there. Subtract 28. -3 divided by 5/3 is -9/5, right? Do that in my head. -1.8. That's right, right? I'm feeling uncertain. Yeah, okay. Normal CDF, -1.8. It's about 0.036 is what you should have gotten. On the power, yes is 1 minus beta, but what does that mean? It's the probability of correctly rejecting the null because you're in the critical region, given that the null is false, the alternative is true. We want high power. Right? We want the test to be powerful. As a prosecuting attorney, we want to be able to convict that person if they truly are guilty. If it's an unethical prosecuting attorney, then they want to convict the person even if they're innocent. Let's not go there. Anyway, yeah, it is 1 minus beta. If beta is 0.036, this is going to be 1 minus 0.036. Will be 0.964. Graphically, and a part of the problem is also to interpret these graphically. shade the region whose area is beta. I haven't done that yet. Beta's type 2 error. You fail to reject the null when the alternative is true. X bar is not in the rejection region. When the purple graph is the true sampling distribution, the probability of that happening is the area under the purple curve to the left of 25. So this red area is alpha. This purple area is beta. Part H says, if the sample size is increased, n is increased, the standard deviation of X bar will decrease. What's the geometric effect on the two curves? This number, as n increases, it gets smaller. So the inflection points move closer to 20 and 28 respectively. These curves get skinnier and skinnier. Of course, to make the area under them still equal to 1, they have to get taller and taller as well. That's the effect on the curves. Part I, if the sample size is increased, but the critical point is not changed, what's the effect on alpha and beta? If we still reject the null when X bar is bigger than 25, what's going to happen to both alpha and beta? What did you say? Yep. And alpha and beta both decrease. And visually, it's because these curves are getting taller and skinnier. And so the area under the green curve to the right of 25 is smaller. And the area under the purple curve to the left of 25 is smaller. If you keep the rejection region the same. Got to be careful though. I mean, if you decide on what alpha should be before you figure out the rejection region, if you decide to let alpha be 0.05, and then you figure out the critical region from that, when you increase n and you keep the same alpha, the critical point boundary of the rejection region changes actually. So it's a little funny if you approach it that way.